Hello, everyone. Thanks, PyCon, for having me. I just sent the abstract, and I was not expecting to have the talk, but then at the end, it happened. So I just finished the presentation now. I'm also really bad at explaining, so bear with me. I put the talk as advanced, but it will not be advanced. It will just be a little bit complex, as you can see from the title. But I guarantee it's just to catch a bit the eye. So I'm going to tell something about me, for who doesn't know me. And I want to tell you why it's important to program sometimes in Python and why all of this is important, why all this talk is important. First of all, I'm from UCL. I'm a researcher at UCL. I'm part of a Marie Curie consortium, Concise, at the end. We have some people here from the consortium, Shiva, and he also did a lot of work on this. So thank him at the end if you like it. But yeah, why is this important? 1 year ago, I basically died. And I was in a coma, and this is what happened. And this was my face, completely destroyed. And this is a reconstruction of a reconstruction. If you know something about CT scans, usually you take a slice, and then from these slices, which are reconstructions, you reconstruct a skull. And then you can reconstruct the person. And most of this technology nowadays, all the research around reconstructing images in biomedical imaging is done most in Python. All the machine learning stuff, all the learn regularization that you apply at the end, it's all done in Python. So sometimes it's nice to look back and say, okay, we are actually saving lives sometimes. So this is nice. What are we going to talk about? I'm going to show you a problem which has nothing to do with CT scans, but it's still applied in biophotonics. And I'm going to show you the data and what's the solution to the problem. And I'm going to try to convince you that it works. So as I told you, you are expecting to see something like this. Like we are shooting lasers with Python, and there is crazy math. But at the end of the day, we are applying some math from thousands and thousands of years ago, and then you put it into a computer, and then you get something like this. You get an approximation. This is what happens if you use float 16. So the problem. In fluorescence microscopy, it's really nice to have a lot of dimensions. So for example, you are interested in the spectrum, you're interested in something called lifetime, and it's really hard to get this data at a high resolution and in like real time or like at a speed that is useful to be applied somewhere in the medical field. So you cannot wait. You cannot have a patient and say, okay, let's take a tissue. The patient is about to die. You need to analyze it. And then after 5 hours, you come back, the patient died. It's not useful. So you need something that goes a bit faster. So the type of data that you can acquire in this field is with two types of cameras. CMOS cameras or CCD cameras and single pixel cameras. And these cameras, the CMOS, is usually high spatial resolution. But it's easy to have a CMOS, and it's not that expensive to have intensity only, so RGB. And you have like a 2000 by 2000 image, which is nice. You also have single pixel cameras, which are, you can reconstruct from these cameras images, which are low spatial resolution. But you can include with several other devices, spectral and temporal resolution for fluorescence, which is nice. So the problem that I want to show you is how you take these two measurements done simultaneously on the same tissue, and how do you put them together? So the CMOS camera, when you take this tensor out of your camera, it's something like this. So it's a 3D. You have a tissue which has like some slices in the depth dimension, and then you have high resolution volume at the end of the day, but you have only intensity information. The single pixel camera, on the other hand, you have very low resolution, like 32 by 32, but you have the addition of this other two dimension, t and lambda. So this is time, and this is spectrum. And here you can see the equivalent, like colored. So this is the spectral information, and this is the lifetime information from the temporal decay. Now, how do we put this together? This is what we are going to analyze. But first, let me show you, because it's really difficult to grasp what this data is. And at first sight, it's kind of hard. So I'm going to do something really ugly for PyCon and show you a Python notebook. And hopefully it will run real time. So this is the CMOS that you saw before. So it's a volume again. So you have 20 slices in the depth. Of course, it's a tissue, so you don't have a lot of depth in reality. It's just on a slice, on a microscope. And then you can have up to 2,000 or 5,000 by 5,000 images, which are really nice. In this case, we downscale it just for the sake of the Jupyter notebook and of this computer. Otherwise, it will explode. And to show you a bit the single pixel camera outcome, it's something like this. You have a 32 by 32 image, color with the spectral information. And for each pixel, you have the spectrum and the time. So if I move up in this orange region, the spectrum is different, okay? And so on. And the time will be also different. And this information is really important because you can actually tell something about the sample itself. So, for example, the temporal decay tells you something about the metabolism of the cell, of the environment, while the spectrum, you can actually identify very easily the fluorophores, among many other things. So the spatial dimensions are not the only things that you want to look at. So how do we acquire this? I'm just going to go quickly through this. It's going to be a bit boring. X and Y, it's really simple. You take a normal camera from your phone and you have an array of detectors, and you have X and Y dimensions. But Z is a bit harder. How do you acquire depth with a microscope and a camera like this? The thing to consider is that higher spatial frequencies attenuate with the focus. So if you illuminate the sample with a pattern of light that has high frequency, you can actually slice really nicely and then get one slice. You move the sample up and down, and you can actually get very nice slices, and then you create this volume. So we do this with 2D sinusoids. And the way to reconstruct is something like this. So for each slice Z, you acquire two images with a different shift of the sinusoids by 2 pi by 3. And then you apply this formula, which includes a Hilbert transform, and you get your slice. This is quite fast. You just have to wait to get enough photons from your sample, and that's it. So the time of the reconstruction is actually nothing. And this is how we get this first tensor, Y CMOS. The second is a little bit more hard, as I told you before. But it's important to notice that it's really cheap to get this type of cameras and this type of measurement. It's just that it doesn't look nice. You cannot see anything from the cells compared to this. But I need to show you how this works. How do we acquire this single pixel camera and what this single pixel camera means? So let's focus on an easier case where we don't have time and lambda, because that's easy to add. We just look at the space. How do you acquire an image in a single pixel detector? You have some light, in this case a laser, that goes into a device called DMD, which can project patterns. It's like it's a set of mirrors, but think of it as a display that you can switch your patterns and create this illumination. So the laser goes into the DMD, the light bounces back, goes into the scene, or in our case, microscopes. So you're gonna have a smaller sample. And then you acquire this information in one single detector, which can be like a photon counter. So you count the number of photons that you have at the detector, and you get one measurement. So from this measurement, you change the pattern, you get a new measurement, and if you do this multiple times, you can reconstruct from these measurements the image. And this is how it works. So let's go once again. You have the sample on the left, and you get some patterns that illuminate the sample, something like this. And for each pattern that you illuminate with, you acquire one measurement. And at the end, see, the more measurements you have, the better the reconstruction. This is nice, and it's important because this is fast. You don't have to acquire to like sample every single pixel in the image to actually have the image, because images are sparse in some domain. And there is a theory of compressive sensing that allows you to do this at sub-Nyquist sampling, actually. So it's really nice. If you don't have noise, you can reconstruct this with almost no measurements compared to the number of pixels. So how does it work mathematically? The first thing that you have, the sample with the pattern, is a dot product. So the measurement itself is physically a dot product between the sample and the pattern. Then the way you reconstruct is with the Roth model. And this is the same thing that was used to get the first image of the black hole that we have. This is exactly the same mathematical problem. And it's very simple. You just minimize this function, which is a fidelity term with your measurements. And this W is the set of patterns that you have, but put in a matrix. And you add this term for regularization, which is called total variation. And you can think of this as a 2D derivative of your image. So you look at the pixels, one next to the other, how it changes, and you add these values all together in a function. And this is really nice. It has been for very long time, 50, 60 years, more, and it still works today. And the way you reconstruct, you have different algorithms to solve this. One is Tval3, which we use in this case, but you can also use something else like proximal gradient descent or something else. And now we add time and spectrum. And to add this, you just need to boost your detector. How do you do this? You can add a spectrometer and then put multiple single pixel detectors, and then you have multiple channels. And this is cheap. You don't have to have 1 million pixels that have hyperspectral information. You just have 16, and then you have a 16 channel image at the end of the day, which is really nice and really cheap. And then you add something called time correlated single photon counter, and you can get the time. So it's just a matter of adding devices in the optical table, and you get this tensor at the end. So the previous one was 3-dimensional. This is 4-dimensional. So remember, we need to put this together. How do you do this? You have to frame it, in this case, as a linear convex optimization problem. And it looks something like this. So we came up with this problem that we want to solve to fuse these two tensors, y CMOS and y SPC. And how do you do this? Well, you need to create this loss function, which basically tells you the first term, you want to compare the CMOS. The second term, you want to compare the single pixel camera. And then at the end, you get this X, which will be 5-dimensional. How, and then you will think, like, how do you do this? Like, why would you even think of this? Well, it works. S, T, and D, in this case, are summations over spectral, temporal, and depth dimensions. And this is exactly why it works, because you can compare X to Y if you perform some transformation, if you project X into the same space of Y. So these operators allow you to do that. And of course, one is high resolution, one is low resolution. So you also need to downsample. So in this case, we want the energy of the tensor at the end of X to be the same as Y, CMOS, and YSPC. So we always sum. We cannot perform average pooling, for example. We need to do some pooling. So it's something like this. So you take over a window, you sum the window together, and then you get a value at the end. Now, the first one is the 3D spatial fidelity. The second is the 4D spectrotemporal fidelity. And how do you solve it? There is an algorithm called linear conjugate gradient, and this is something developed 75 years ago, and is the best to solve this problem. How do you do this? The algorithm is supposed to solve a linear system like AX equals B. But you need to transform this function into something like that. So how do you do this? Well, you compute the gradient by hand, and you put it to 0, because it's the optimality condition. If you do this, and you follow all the steps, you perform the gradient over the loss function, you end up with something like this. This first term is AX. The second term is B. And now you can solve this. Of course, if you're lazy, you can always do Adam and backpropagation, but Adam and backpropagation, this problem takes 8 iterations while CG 10. So sometimes it's nice to use something else. So let's recap quickly. We have this CMOS acquired data with this structured illumination microscopy technique. We have the SPC. We perform total variation for each time and for each spectral channel. We get these two tensors. We normalize them. And then at the end, we perform this data fusion algorithm by minimizing that function. So what I want to show you is how do you put this math in code and create like a synergy of this math and Python. It's actually really simple. Don't look too much at the code at the end because it's not really nice. But I'm going to try to show you why it works and why you can write math directly in Python. If you do something like this, you can create a class like this sum operator. You instantiate it with some parameters. And then you have, if you check before the derivative of that function, you have to actually create also some transpose operations for each of these classes. So in this case, you have this T, which if you sum over one dimension, when you go back, what do? You take that value and then you repeat it along that dimension as many times as many dimensions you have. So this is why it's actually nice. You can write this, and then when you go and actually write the problem, you can do something like this. We have the A and the B, and then you can basically write the math as it was in the presentation in code. And this is quite nice in my opinion. So at the end, when you optimize that, you get this tensor at the end. So it's high resolution in everything, in spectrum, in time, and of course in intensity as the beginning. And you have these 20 Zs, 20 slices that you can look at very high resolution. And I just want to show you how fast it is on this computer. So if you run the algorithm, it's going to converge around 17, 18 steps. This runs on, everything runs on PyTorch on MPS right now, so it's quite fast. But yeah, and it's done. So this is quite fast. So I'll try to conclude so that we have time for questions. I want to convince you that this works. Because of course, I showed you some code, I went really fast. Probably the data is really hard to understand, but I want you to convince that this is actually something that works. So this is the output of the algorithm. We have it in spectrum, in time, and in intensity. And to convince ourselves that it actually works and we did something that is nice, we have to zoom in a region. Because of course, we fused something that was high resolution with something low, and you want to check in a very small region that everything matches. So what you do, you zoom, and then you look at the spectrum and at the time. There is a way to get a ground truth of the same region with the hardware. So you can actually compare. And this is exactly what we did. Here we have the ground truth, and on the left we have the data fusion output. And then we can zoom even more to be sure that it works and say, okay, the spectrum is the same for the ground truth and the data fusion, and the time the same. Actually, for time, we are interested in this lifetime of this curve, of this mono exponential, mono decay. And it's really close. And if you compute, for example, PSNR and SSIM, you'll see that it's really close. And nice thing, if you have the CMOS camera information, you can see that we actually do also some denoising. So it's nice. And thank you, everyone. I hope it was not too much.
Okay. Do we have some question?
So thank you for the presentation. I found it really interesting because I come from your same field, just on the opposite side. So I also come from fluorescence microscopy, and totally unrelated, but one of the most tedious tasks of sharing that kind of data is formatting the data. And what formats do you use? Have you converged on standards like OME, OMXML, OMETIF, OMEZAR, or do you come up with your own?
Okay, this is a really tough question. A really nice question. So for now, this data, we put it on Zenodo as just NumPy arrays. With, yeah, it's each acquisition is, if you go to this QR code, we'll bring you to Zenodo, and you basically have just the two tensors in a NPZ file. Yeah, it's something very rough, but it's just two acquisition. We have these cells and some beads. So yeah, the problem is, of course, let's say you want to make a data set of this, it's gonna be really hard to to continue using NPZ files. So you need something different. Yeah.
Okay, we have another question. How will you say Python aids in solving this problem? Is it mainly PyTorch?
It's the synergy of all these things. And for me, Python is something that the value that is added from Python is mostly from the community. So you have in Python, you can do everything. And this is why it's nice. The community is so big and so open, you find a package to do everything. So I think it's nice for this. And yeah, of course, like the computational part is mostly done in PyTorch. So on that aspect, yes. But for example, it's also a language that people can learn really quickly. So for example, we work with surgeons, we work with physicists, we work with people in biology, and you want to show some code at the end. And of course, if you go and show C++, no one will understand. But everyone has seen a bit of Python. So when you have like something with this multidisciplinarity, I would say Python is the way to go. And you actually solve the problem because you have people around it that can understand it. So it's not only PyTorch. It's the community plus PyTorch plus Python.
Totally agree. Another question, how do you move the sample? Stopper motor, how precise is the movement?
The stepper motor, I think, in the depth dimension, well, we move by 1 micrometer for each slice. So the problem is, if you move less, the stepper motor is more precise, but if you move less, then it's harder to get a nice slice. So I think Shiva is the person to actually answer this, because he's the physicist. But the slices overlap, yeah. There is a depth of field that comes from this technique that we use to get the slices. So it's not actually a zero slice, like it's still some, it takes a total of like 1 micrometer, 2 microns, yeah, in Z. So you have to move a bit.
Yes, but we do use stepper.
Yes.
Do we have another question from?
Yeah, thanks a lot. First of all, is everything fine with you right now? Like, because you showed us like the before and the after is here. So,
Yeah. Now
Okay.
it's fine. Well, the titanium stays.
Sorry?
But the titanium, is
stays,
still there,
as Wolverine says. Okay. Sorry, maybe I missed it, but about the pattern that you used,
Yes.
are they coming from the theory? Is just like a random patterns? Is there any way to? It's like a basis that you're.
Yes.
It's a basis.
So
okay.
yes. So what people have been doing since like 6-7 years ago, they were relying on something called the Hadamard basis. So it's like a Hadamard matrix that you reshape into patterns like this. So these are actually Walsh-Hadamard patterns. So you project one in this direction, one in this, you create like a 2D Hadamard transform. But you can use machine learning to actually learn what's the best patterns for your data. So that's what we are also doing. So yeah, that allows you to compress a bit more.
Okay, we have another question. Could you use linear optimization Python package like Pyomo for this problem, or is PyTorch more fit for this purpose?
Well, in this case, so if I go here, this is framed as everything is kind of like vectorized, like if you look at the math, but it's nice to have this in the computer as PyTorch tensors or NumPy arrays. What happens if you use, like, for example, SciPy or something that's usually employed to do linear optimization, and you have a tensor, it's kind of harder to deal with. I think it would work. You just have to linearize all of this and then write ST, R, and D in such a way that works in a vectorized version of the tensors. But yeah, I think it would work. This was just quite fast at the first try with PyTorch, so we kept it.
We have just more time for another question. Thank you so much,
Okay.
Christian.